Hi, welcome to the video preview of our research on design of optimal INS monitor for GNSS spoofing detection using Spoofer's tracking error. In recent years, there has been an uptick of GNSS spoofing events all across the world. GNSS spoofing needs to be detected and mitigated as it could lead to catastrophic events. We focus on the most difficult to detect spoofing scenario where a user is targeted by the spoofer. The spoofer sends a higher powered synchronized spoofing signal. Once the user locks on to the higher powered false signal, the spoofer slowly deviates the user along a dangerous trajectory. We propose utilizing an auxiliary sensor, which is an IMU, to detect spoofing. The IMU is hardwired to the system and is therefore not susceptible to spoofing. Inside a rightly coupled INS-GNSS system, the Kalman filter innovations can be looked at for any discrepancy between GNSS and INS to detect spoofing. The spoofer needs to continuously track the user position to generate spoofing signals. For detection, we leverage the fact that the spoofer will always have some position tracking error. This tracking error can allow for detection even before the spoofer sends any position offsets. As a starting point, we model the spoofer's tracking error as zero mean white Gaussian noise in a single spatial direction. This noise appears as the additive term, which is the only difference between authentic and spoofed GNSS measurements. Since innovation is the first place where the INS and GNSS are compared, the tracking error will first appear in the innovation vector. If authentic innovations are represented as shown here, then spoofed innovations include the additive noise term. But just looking at instantaneous innovations might not be enough for detecting small tracking errors. We therefore derive an optimal test statistic using the Neyman-Pearson lemma, which maximizes probability of detection. First, we transform the innovations in the position domain and then cumulatively add these normalized position domain innovations. We also derive the misdetection probability, which allows us to quantify the performance of the monitor. Thus, given misdetection requirement PMD, we can determine the minimum accumulation time and min to ensure detection of tracking error variance larger than sigma t squared. The results of this parametric study from the previous equation allows us to visualize the performance of the monitor as a function of accumulation time n and tracking error standard deviation sigma t. We also show that the performance is quite comparable even for different grades of IMU. We also analyze the performance of the monitor for colored noise. Although color tracking error is difficult to detect as compared to white tracking error, a longer accumulation time achieves the desired misdetection requirement. In summary, the monitor detects spoofing within seconds at the earliest stage using only spoofer's tracking errors with low misdetection rates. If you have any questions or comments, please feel free to contact me at this email. Thank you.